Volumes with known cross-sections. Cross-section. A cross-section of a solid object S is the plane region formed by intersecting S with a plane. Informally, a cross-section is a slice of a three-dimensional object. This is probably best understood by looking at a picture. So here I have a solid object S and a cross-section located at this value x here can be obtained by thinking about taking just a sheet of paper and slicing this particular solid. So right at this location x, my cross-section appears to be a square, and we're going to call the area of that cross-section A of x. It's dependent upon the x value location that I decided to take my slice. Here I have a second solid, and this time the cross-section at this location here x is a triangle instead. So we can see that the cross-section's area is going to vary based on the value of x chosen. So if I chose my x location over here, I still have a triangular cross-section, but the area is different. We're interested in finding the volume of these three-dimensional objects. To find the volume of the solid, we can think of adding infinitely many of these infinitely thin cross-sections together. So we are taking the limit as n approaches infinity. N is the number of cross-sections. So if the number of cross-sections goes to infinity, and we think about adding, so summation notation, we're adding all of those areas together. So if we add these infinitely many, infinitely thin cross-sections together, we will obtain the exact volume of these solids. Let's go ahead and extend the previous idea. Volume with cross-sections perpendicular to the x-axis. Suppose that a solid body extends from x equals a to x equals b. Let a of x be a continuous function that gives the area of a vertical cross-section at x, perpendicular to the x-axis. Then the volume of the solid is given by v equals the integral from x equals a to x equals b of a of x dx. So again, looking at the previous image, if we want to find the volume of this solid extending from x equals a to x equals b, then we need only find a way to represent the area of a cross-section as a function of x. And then we're going to set up this definite integral which will yield the exact volume of the solid. Let's go ahead and look at our first example. A shape is formed by taking infinitely thin squares and stacking them up perpendicular to the x-axis with base formed by the lines y equals 1/2 x, y equals negative 1/2 x, and x equals 2. Find the volume of this shape. Let's start by constructing the base and sketching these three lines. Here I'm going to go ahead and label them as y equals 1/2 x, y equals negative 1/2 x, and x equals 2. So this is going to be the base of my solid, and I'm told that the cross-sections are going to be squares that are perpendicular to the x-axis. I'm going to construct one of these squares at this generic location x. So I'm going to create a square that is perpendicular to the x-axis. Remember, this square is coming out at us, so it's going to make a three-dimensional object here. I'm going to try to make it look like it's popping out of the screen a little bit. So here is my square, not quite perfect. And notice that the side of the square here touches both the top and bottom function here, and that's the side length of the square. So I'm going to go ahead and call that s of x. That's going to be this length right here. Before going any further, let's go ahead and take a look at a 3D image on Desmos to help us really visualize this. All right, here it is. So let's go ahead and sort of move it around a little bit, which is really nice. So we have here's the origin. So we have 1/2 x, we have negative 1/2 x, and so we can, if I'm looking at it straight down, then I can see these right here are going to be those squares. But if I change the perspective, then I can see a couple of these squares here. So the base is perpendicular to the x-axis. So here's my x-axis. So they're kind of sticking up at us, and they change in size as I move along because the base is getting bigger as I go from 0 to 2. Let's increase the number of subdivisions slowly, and I can see that solid that's being formed as I increase the number of, in this case, squares. So I'm going to stop there and just change the perspective again. So it's starting to look more and more like a solid, but then we see that one representation of a single cross section there being a perfect square. And if I turn it and look directly at it this way, I can see that square. So that's what we're trying to do. We're trying to add up those squares as I move from 0 to 2. So this b value is 10, our b value will be 2. Now let's go ahead and apply our volume formula. The volume of this solid is going to equal the integral from x equals a to x equals b. Our limits of integration are coming from the x-axis. This region extends from x equals 0 to x equals 2. And the area of my cross-section is side squared. The area of a square is side squared. So here I'm going to go ahead and write brackets squared dx. What goes inside those brackets is s of x. S of x being the side length at any particular x. So what's going to go right here is my side length as a function of x. Well, that's obtained by doing top minus bottom. So 1/2 x minus negative 1/2 x. So I like to include variables in my limits of integration because I want to make sure that I'm consistent throughout the problem, that I'm using the same variable. So here I have 1/2 x minus negative 1/2 x, which combines to just be x squared dx. So the integral that I'm evaluating is simply the integral from 0 to 2 of x squared dx. So now the antiderivative is x cubed over 3 evaluated from 0 to 2. So 2 cubed over 3 minus 0 cubed over 3 is simply 8/3. Because we're finding a volume, our units would be units cubed. Volume with cross-sections perpendicular to the y-axis. Suppose now that a solid body extends from y equals c to y equals d. Let a of y be a continuous function that gives the area of a horizontal cross-section at y, perpendicular to the y-axis. Then the volume of the solid is given by v equals the integral from y equals c to y equals d of a of y dy. So notice the only difference here is that the volume formula is in terms of y, and that's because our cross-sections are perpendicular to the y-axis. So our limits of integration are y values, so y would extend from y equals c to y equals d, and our cross-section would have to be written as a function of the variable y. In this example, we're told the base of a solid is bounded by y equals x cubed, y equals 0, and x equals 1. Sketch the base region and set up the integral needed to find the volume V of the solid with the following cross-sections. In part A, we're going to have semicircles taken perpendicular to the y-axis. We'll start by constructing the base. The base is bounded by y equals x cubed, y equals 0, and x equals 1. So y equals x cubed passes through 0, 0, and 1, 1, and has this general shape. So I have y equals x cubed. Y equals 0 is simply the x-axis. And then x equals 1 is a vertical line at 1. So I have x equals 1. So this right here is my base region. And I'm told that my cross-sections are semicircles that are perpendicular to the y-axis. So I'm going to go ahead and sketch one of these cross-sections. So perpendicular to the y-axis is going to make my shape look something like this. This is my semicircle that again is sort of popping out of the base to create a three-dimensional solid. And so this cross section here, this base of my cross section is actually the diameter of the semicircle. So I'm going to have to represent the diameter as a function of y because my cross sections are perpendicular to the y-axis. And this is going to extend from y equals 0 to y equals 1. Because remember, my limits of integration now have to be y values. So let's go ahead and start to find our volume by applying the formula here. So our volume is going to equal the integral from y equals 0 to y equals 1. And then we're going to need the area function for a semicircle. Well, a semicircle is 1/2 pi r squared. So I'm going to go ahead and put 1/2 pi, and then I'm going to leave a big blank space for a second, squared dy. So what's going to have to go right here is the radius as a function of y. So here, this is the diameter as a function of y. So I'm going to have to find the diameter as a function of y and cut it in half to find the radius as a function of y. So I'm going to go ahead and just start by putting over 2. So what's going to have to go in the numerator here is the diameter as a function of y. Well, this diameter is going to be obtained by doing the right function minus the left function. Well, the right function here is x equals 1. So I'm going to have 1 minus, and now here we have to be incredibly careful. So here, if we were to just think that the left function over here is x cubed, and we put x cubed right here, that would be incorrect because we need everything to be in terms of y. And that's why I try to keep the habit of starting with variables in my limits of integration. I have to rewrite this function in terms of y. So if I take the cube root of both sides, I'll have x equals the cube root of y. So my diameter, right minus left, is 1 minus the cube root of y. So this right here is my radius. So it's the diameter as a function of y over 2. So this is my answer for this problem because we were simply asked to set up the integral needed to find the volume V of the solid. In this example, we're going to use the same base, but this time the cross sections will be isosceles right triangles with base as the hypotenuse taken perpendicular to the x-axis. So I'm going to go ahead and construct one of these isosceles right triangles. So here I'm going to pick some generic x value and construct my base that is perpendicular to the x-axis. So this is going to be a isosceles right triangle. So this is a right angle right here, and we're told that the hypotenuse lies along the base of the region. Alright, so we'll go ahead and start to apply our volume formula here. So our limits of integration will be x values. So we're going to have x equals 0 to x equals 1. And we're going to need to find the area of an isosceles right triangle here. So this, again, is the hypotenuse. So this is the base of my triangle. So I'm going to go ahead and call it b of x. And we can find that doing top minus bottom. So that would be x cubed minus 0. So the formula for a triangle in general is 1/2 base times height. So my base will be x cubed minus 0, so this is b of x. And then what's going to need to go right here is the height as a function of x dx. So we have 1/2 base times height. Here's my base. I need to go ahead and think about what is my height going to be for this particular isosceles right triangle here in terms of x. So I'm going to go ahead and construct my right triangle over here, my isosceles right triangle, so we can get a better sense of what's going on. So this is my base, b of x, and this is an isosceles right triangle, so that means that if this is 90, then these two are each 45 degrees exactly. And I'm interested in finding the height, h of x. So here, if I go ahead and construct this perpendicular, this angle bisector here, this is going to be 90 degrees, and if this angle right here in the corner was 45, this angle up here must also be 45. In other words, this is also a isosceles right triangle, so that means these two side lengths are the same. Well, if I cut this base in half here, then this is b over 2, so that means that the height is also b over 2, or b of x over 2. So that's what I'm going to go ahead and fill in right here for h of x. It's going to be the base over 2, so it's going to be x cubed minus 0, the base, divided by 2. And we'll go ahead and clean this up a little bit. This is going to be the integral from 0 to 1, and then we have 1/2 and then another 1/2 over here, so we have 1/4, and then we have x cubed times x cubed, that's x cubed squared dx, or x cubed squared is just x to the 6th dx. So this is the integral that will find me the volume of the solid. In this example, we have a solid is formed with circular discs as cross-sections perpendicular to the x-axis whose diameters run from the parabola y equals x squared to the parabola y equals 2 minus x squared. Set up the integral needed to find the volume V of the solid. So we'll go ahead and zoom in on the picture. So here we have our disc, and we're told that the diameter, so I'm going to go ahead and mark the diameter here, extends from x squared to 2 minus x squared. And I'm going to go ahead and call the diameter here d of x. So the diameter would be top minus bottom here, so it looks like it would be 2 minus x squared, or 2 minus 2x squared would be the diameter of my disk. So we're going to go ahead and find the volume of the solid obtained by having these cross sections where the diameters go across this base region. So now we're going to go ahead and start to set up the volume formula. The volume is equal to the integral from x equals, so we need to know the x values that this region extends, and that's going to be finding the x values of the points of intersection here. So remember, if we want to find the point of intersection, or points of intersection, we're going to need to set the two functions equal to one another. So we'd have 2 equals 2x squared, or x squared equals 1, so we get plus or minus 1. So our limits of integration are going to extend from -1 to 1. And our cross-section is going to be a disk, which is really just a circle. So here we can see that it doesn't look like a circle. We can see here a disk with a height involved, so like a little cylinder with a height. But as we saw, we're going to go ahead and think about these as infinitely many, infinitely thin cross-sections. So we are going to have the area of a circle here as our area function. So the area of a circle is pi r squared. So I'm going to leave pi, I'm going to leave a big space for r squared. So what needs to go right here is my radius as a function of x. Well, here we found that this was going to end up being the diameter. So the diameter, 2 minus 2x squared, is going to have to be cut in half to find the radius. So my radius is going to be 2 minus 2x squared over 2. And then we have dx. We want to make sure that we're all the same variable here, our limits of integration and our integrand and our differential. So this is going to be the integral needed to find the volume of this particular solid. So if we clean it up just a little bit, we have the integral from -1 to 1, and then we have pi over 4, and then 2 minus 2x squared dx. So the 4 is coming from taking the 2 and squaring it and bringing it to the outside, and then I left the 2 minus 2x squared, quantity squared, here. So evaluating this definite integral will give us the volume of our solid. Now, when solids are formed by cross-sections that are circles, we can think of them as being created by rotating or revolving a two-dimensional region about an axis. And these are called solids of revolution, which is what we're going to go ahead and study next.